Hello everyone, welcome to a video that will introduce an issue that arises in probability known as DeMorgan's laws. The book that we're using is Introduction to Probability, 2nd edition by Blitzstein and Hwang, and you can actually download this book for free from the internet, and you see the link here at the bottom. So we will be looking at some material from chapter 1, but in fact we're not going to do all of chapter 1. We're going to be doing a bit from section 1.2 on sample spaces, and we'll look a bit at unions and intersections and complements, and then close with DeMorgan's laws, which relate unions and intersections and complements in an interesting way. Some of you, if you've encountered logic, may have seen DeMorgan's laws where you get basically the same kind of thing in terms of and, or, and not. So if that's familiar to you, great, then you've got a head start. If it's not, then this will give you a head start for your encounter someday, perhaps, with logic. So it works well either way. So the Blitzstein and Hwang example that they use, they call Pebble World, is this collection of 9 circles, which are supposed to be the elements in some set S, which is our sample space. Now I'm going to give these elements numbers, so I'm going to call them 1, 2, 3, and so on, all the way up to 9. So they are illustrating graphically what's going on. I'll be able to do some more explicit calculations by giving these elements these names. Okay, so you can see now that the set A consists of, and I write this curly brace, 1, 2, 3, 4, 5. Sometimes I have a few more squiggles. Anyway, it's still intended to be a curly brace. Okay, so that is set A, and so I've just taken all of the numbers that you find there. And I wrote them in order 1, 2, 3, 4, 5, but that's actually not important in a set. In a set, there are 2 things that are important. Either something is in it or something is not in it. So you'll notice that 6, 7, 8, and 9 are not in set A. Something else that does not matter is the order. So I could have written this set as in curly braces 5, 4, 3, 2, 1, and that would be the very same set, because all that matters is membership, being in the set or not. There's no notion of order. There are other things in mathematics that pay attention to order, but sets are not one of them. And so sets are often just the right tool that we need, and they are very widely used, so that a lot of things can be said well in terms of sets. So I've shown set A already. Here is set B, and you will notice the elements are what? 6 and 5 and 8 and 9. Basically, I want everything that's in blue. So everything that's in blue I'll write in here. And to keep things simple, I'll put leave everything in red. So these are my elements in set B. Now there's another set that's really important, and that is this Pebble World. So this is called, if we're going to be talking about probabilities, we're going to be talking about samples, and then we'll talk about a sample space. Anyway, there is some large set which, for our purposes, includes what we will treat as everything, our universe, our entire world, So, all the things that can happen, and which in this case will be 1, 2, 3, and so on, all the way up through 9. And again, remember the order doesn't matter in the set. And I couldn't sensibly try to add the number 2 again to this set and get anything different. I mean, I could try to add it, but with the rules of sets, adding means turns into union. But if you take the union and you're trying to add something that's already there, then it just makes no difference because it's already in there. Okay, so here are 3 sets that we can take a look at, and then we can do various interesting things with them. We can, for example, combine sets. We might say try uniting them, and if we unite 2 sets, then the result that we get is a union, which conveniently we represent using a symbol that looks like the letter U. It's a little small, but basically it looks kind of like a U. So the union of A and B will be everything that is in A along with everything that is in B. And if something is in there twice, well, we just write it down once, don't we? So I'll take all of my elements from A, and then I'll take a look at B and ask myself, well, what else do I need to include? So I've already got 5, so I don't need 5. I've got 6. Notice that I do not have 7. 7 is not in either one of these sets, but I've got 6, 8, and 9 that enters in to my union on account of B. It was not already A. Now, of course, you could say, well, I got 5 from B. It doesn't really matter. So that's our union. Okay, so that's our union. It contains everything that is in A along with everything that's in B. And if something's in there twice, well, we only include it once. We could also talk about the intersection, and we write that with, well, it's like an upside down U, I suppose. A intersection B, which means we look for everything that is in both A and B. Now, if we do that, we'll notice what? 1, 2, 3, and 4 are not in B. 6, 8, and 9 are not in A, so those are not going to be in our intersection. The one element that they have in common is 5. So does that mean our intersection is 5? Well, not quite. I've already said it right in curly brace. Our intersection is the set containing 5, which is not the same as 5, because 5 is not a set. So there we go. We have the union and the intersection. Now, since we've got this sample space S, there's something else we can do, and that is we can take a complement relative to S. So we can remind ourselves of what the union of A and B is. So I'll write that again quickly. 1, 2, 3, 4, 5, 6, 8, 9. Now you remember our sample space S. So if I have this, which is counting as everything, it's the set including the numbers 1 through 9. So if I want the complement, that means I want everything that is in the sample space S that is not in A union B. So I can thank you, Adobe. I can write that by putting a little C here, and I've got the parentheses so that you know that the complement applies to the whole thing A union B. So now I want everything that is in S, which recall was what 1 up through 9, that is not an A union B. But A union B, you'll notice, is everything in S except for 7. So our complement here is simply 7. Okay, so that's the complement. Now I can look at the complement of the set A, which means everything that's in S is not in A, and that complement is just 6, 7, 8, 9. And I can also look at the complement of B, and that is what? 1, 2, 3, 4. Remember, it's everything outside the blue square. And then, don't forget, 7. So, those are the complements of A and B. Now I can ask myself, how does the complement of something built out of A and B, like the union or the intersection, relate to the individual complements? And that, well, DeMorgan's law will give me some insight there. So I'm not going to prove DeMorgan's law. I'm actually going to illustrate it. And part of how I'm going to illustrate it is by seeing what would happen if you maybe make a tempting mistake. Let's suppose we just try taking the union of these two. So maybe I think, well, I just take unions, and everything's going to be unions, and I'll get something nice out of that. Let's see. So if I take the union of A complement and B complement, then these two sets that I've just written here. So I need everything that's in at least one of these sets. So 1, 2, 3, 4, 6, 7, 8, 9. Now you will notice that this looks nothing like the complement of A union B. So if you're kind of in a hurry and you just wrote some symbols down and you thought it should be all unions and complements, well, you now see that this is very definitely not the same as this. So we're not going to find a nice formula that relates the complement of A union B to the union of the complements. But we can do something else. We can take a look at the intersection of these two complements. A complement intersection B complement, which means I want everything that is in both of these sets. There's got to be in the one and in the other. So let's see here. What is it that is in this intersection? What's in both of these sets? Well, it's not going to involve 1, 2, 3, or 4, because those aren't in A complement. And it's not going to involve 6, 8, or 9, because those are not in B complement. So all we get is 7. And of course, this is not the number 7. It's the set containing the number 7 and only the number 7. And now you will notice that this thing here and this thing here are equal. And so our general rule, which I have illustrated in this one case, is that A union B complement equals A complement intersection B complement. So if I had a union in one place, then I get an intersection in the other place. Now in words, this says whatever is not in the union of A and B, or if you like, whatever is not in at least one of A and B, is whatever is not in the complement of A and also not in, whatever is not in A and also not in B. So if I had a union in one place, then I get the intersection for the other. So this is similar to logic, where union is like and intersection is like or. Although or is a bit tricky in logic, actually. I could make another video about that. Because of inclusive versus exclusive interpretations of or. Anyway, so that is one of DeMorgan's laws. Now I want to talk about the other of DeMorgan's laws, but first I'll say a little bit about DeMorgan's laws. So De Morgan was a 19th century British mathematician. He didn't invent these laws, but he applied them in a way that was memorable and useful in a new context. The laws in the context of logic go back to Aristotle, at least in 300-something BC, and were well known among Latin using medieval scholastic philosophers in Western Europe. I imagine they were known in other parts of the world as well that inherited the Greek philosophy, as in like in the Islamic realm. So it's not like De Morgan invented these, but I guess there's hope. Maybe if you use something that's been known for 2,000 plus years in a new way, maybe you can get credit for it as well. Okay, so what is the other? What's the other of De Morgan's laws? Well, we can take a look at the intersection of A and B. So I've got a intersection B, and that, as you can see, for example, from looking at this diagram over here, is whatever is in the weird irregular red box with the corner cut off, and also in the blue box, and that is just the element 5. So does that mean my intersection is 5? No, it means it is a set containing 5. Now I can take the complement of this set and then see what it is that I get. Recall the complement is always relative to the sample space, my sort of universe of what there is, which is just the set containing the numbers 1 through 9 in this case. Now, what is in that set that is not in set containing 5? Well, it's 1, 2, 3, 4, 6, 7, 8, 9. Okay, so I can also take a look at the complement of A, which, as you'll notice from here, is 6, 7, 8, 9, all bundled together in a set. 6, 7, 8, 9. And I can take a look at the complement of B, and again, looking at my diagram, I want everything that's not in the blue box. So 1, 2, 3, 4, 7. Okay, now I can try taking the intersection of these two complements and see if I get anything interesting. So recall the intersection is the upside down U symbol. So this means I want what? Everything that is in this set and also in this set. Now, I don't find 6, 8, or 9 in B complement. I don't find 1, 2, 3, or 4 in A complement. The only thing they have in common is 7, and so I get the set containing 7, and only that as the intersection of these. Now that doesn't look anything like the complement of the intersections, does it? So there's no nice rule there. But what if I take a look at the union of A complement and B complement? That means I want everything that is in at least one of these sets. So that's 1, 2, 3, 4, 6, 7, 8, 9, isn't it? 2, 3, 4, 6, 7, 8, 9. So it's everything in my sample space other than 5. And so now I can compare this to what I have here, and these are the same, aren't they? 1, 2, 3, 4, 6, 7, 8, 9. 1, 2, 3, 4, 6, 7, 8, 9. And so I have an illustration of DeMorgan's law, A intersection B complement equals A complement union B complement. So in words, you could say that whatever is not in both A and B is the same as whatever is not in A along with whatever is not in B. Now, one further amusing factoid, a little more advanced, is if you like, you could derive one of these rules from the other. So there's really only one in the sense if you can take the complement of a complement and get back where you were. So there we go. We have DeMorgan's laws illustrated, and we have avoided a perhaps tempting misunderstanding along the way. Thank you.